Welcome friends. In this session we discuss the various mathematical forms of linear programming problem and their association with convex set etc. First of all, linear programming problem in matrix form. In general mathematical programming problem of optimizing f of x subject to the constraints g(i) of x less than or equal to 0 for I equal to 1 to etc. m for x greater than or equal to 0, when the function f of x and the constraints g(i) of x for I equal to 1 to etc. m all are linear, the problem is linear programming problem. The problem is f of x is here subject to the constraints g(i) of x less than or equal to 0 for I equal to 1 to etc. m x greater than or equal to 0. Then if g(i) of x all are in linear form, the problem is a linear programming problem. So, the problem of LPP is to find an optimal, that is minimum or maximum value of a linear function, that is f of x subject to the linear constraints as optimize f of x that is equal to c1 x1 plus c2 x2 plus etc. plus cn xn subject to a11 x1 plus a12 x2 plus etc. plus a1n xn less than or equal to b1, then a21 x1 plus a22 x2 etc. plus a2n xn less than or equal to b2 etc. a m1 x1 plus a m2 x2 plus etc. plus a mn xn less than or equal to bm, where x1 x2 etc. xn x1 x2 etc. xn all are greater than or equal to 0. In matrix form, the linear programming problem can be written as optimize f of x c1 x1 plus c2 x2 etc. plus cn xn, that is equal to c into x subject to a into x. These are the constraints a into x less than or equal to b, where x greater than or equal to 0. Here a equal to the matrix containing elements a11, a12 etc. a1n, a21, a22 etc. a2n etc. am1, am2 etc. amn. This is the matrix A, and B equal to the column matrix b1, b2 etc. bm, and C equal to the row matrix c1, c2 etc. cn, c1, c2 etc. cn. Okay. X equal to column matrix x1, x2 etc. xn transpose, x1, x2 etc. xn transpose. Here CJs are called the cost coefficients, that is C1, C2 etc. Cn, they are called the cost coefficients. Now we are moving to the general linear programming problem. Consider the linear programming problem optimize f of x, that is equal to c1 x1 plus c2 x2 etc. plus cn xn, then subject to the constraints a11 x1 plus a12 x2 etc. plus a1n xn less than or equal to b1 or greater than or equal to b1 or equal to b1 and second constraint a21 x1 plus a22 x2 etc. plus a2n xn, that also less than or equal to b1 or b2 or greater than or equal to b2 or equal to b2, and a m1 x1 plus a m2 x2 etc. plus a mn xn less than or equal to bm or greater than or equal to bm or equal to bm, where x1 x2 etc. xn are greater than or equal to 0. Then the problem of determining the n tuple x1 x2 etc. xn, which makes f of x a maximum or minimum satisfying the given set of constraints, is called the general linear programming problem. Then the next is canonical form of linear programming problem. The general linear programming problem can always be put in the form maximize f of x is equal to c1 x1 plus c2 x2 etc. plus cn xn, subject to a11 x1 plus a12 x2 etc. plus a1n xn less than or equal to b1. Next a21 x1 plus a22 x2 etc. plus a2n xn less than or equal to b2. Finally, am1 x1 plus am2 x2 etc. plus amn xn less than or equal to bm, where xi values are greater than or equal to 0 for I equal to 1 to etc. n. This form of LPP is known as the canonical form of LPP. The characteristics of this form are: the objective function is of maximization type. Minimization of a function is equivalent to the maximization of its negative expression. All the constraints are of the less than or equal to type, except for the non-negative restriction. All the variables are non-negative. Any unrestricted variable can be written as the difference of two non-negative variables. Next is slack and surplus variables. A linear constraint of the form summation j from 1 to n aij xj less than or equal to bi can be converted into equality by adding a new non-negative variable to the left hand side of the inequality. Such a variable carries a numerical value which is difference between the right and left hand side of the inequality and is known as a slack variable. In a similar way, the non-negative variable subtracted from left hand side of the inequality of the form summation j from 1 to n aij xj greater than or equal to bi for converting into a equality is called a surplus variable. Next is the standard form of linear programming problem. Using the slack variables x n plus 1, let it be x n plus 1, x n plus 2 etc. x m plus n or n plus m. The optimization problem given in the matrix form can be rewritten into optimize f of x, that is equal to c1 x1 plus c2 x2 etc. plus cn xn plus 0 into x n plus 1 plus 0 into x n plus 2 etc. plus 0 into x n plus m or m plus n, subject to the constraints a11 x1 plus a12 x2 etc. plus a1n xn plus x n plus 1, that is equal to b1, and a21 x1 plus a22 x2 etc. plus a2n xn plus x n plus 2, that is equal to b2, and finally a m1 x1 plus a m2 x2 etc. plus a mn xn plus xn plus m or m plus n equal to bm, subject to or the non-negativity constraints are xi greater than or equal to 0 for I equal to 1 to etc. m plus n. That is to optimize in matrix form, that is to optimize f of x is equal to cx subject to ax equal to b where x greater than or equal to 0. Here the matrix C, that is equal to the row vector C1, C2 etc. Cn, then 0, 0 etc. 0, and A equal to the matrix containing the point A11, A12 etc. A1n, then 1, then 0, 0 etc. 0. Next is A21, A22 etc. A2n, then 0, 1, 0 etc. 0, and finally AM1, AM2 etc. AMN 0, 0 etc. 1. And x, that is equal to the column vector x1, x2 etc. xn, then xn plus 1 etc. xn plus m or xm plus n transpose, and b equal to the matrix b1, b2 etc. bm column vector b1, b2 etc. bm the transpose, and xi greater than or equal to 0, and xi greater than or equal to 0 for I equal to 1 to etc. m plus n. This form of linear programming problem is called its standard form. The characteristics of this form are: number 1, all the constraints are expressed in the form of equations except for the non-negative restrictions. Except for the non-negative restrictions, all the constraints are of equality form. The right hand side of each constraint equation is non-negative. Consider a system of m linearly independent equations Ax equal to b for x greater than or equal to 0, where A equal to A11, A12 etc. A1n, A21, A22 etc. A2n etc. AM1, AM2 etc. AMN, and B equal to B1, B2 etc. BM transpose, and X equal to X1, X2 etc. Xn transpose. Here we are considering n variables in m equations. M equations are here and n variables are here, x1, x2 etc. xn, where m less than n. M is less than n. A vector x satisfying the equation Ax equal to b, a vector x satisfying the equation Ax equal to b for x greater than or equal to 0, that is called feasible solution of this system. Feasible, then such an x is called feasible solution of the system. In this system of equations, if any of n minus m variables are given the value 0, the remaining system of m equations in m unknown may have a unique solution. This solution along with the assumed zeros is a solution of Ax equal to b. It is called a basic solution. Such a solution is called a basic solution. It is in basic solution, the n minus m variables are given the values 0, and then using the remaining m equations in m unknowns solved and getting a unique solution for the remaining variables, and that solution is called a basic solution. The m variables remaining in the system after n minus m variables have been put equal to 0 are called the basic variables or simply a basis. Basic variables or simply the basis. The rest of the variables may be called non-basic variables. Since the unique solution of m equations in m variables may also contain zeros, a basic solution contains at least n minus m zeros. If the number of zeros in the basic solution is n minus m, then the solution is called a non-degenerate basic solution. Such a solution is called a non-degenerate basic solution. And if it is greater than n minus m, the solution is said to be degenerating. The solution is said to be degenerating. In a basic solution, if all values of xj's are greater than or equal to 0, then the solution is called basic feasible solution. If all xi values are greater than or equal to 0, it is called basic feasible solution. A basic feasible solution which optimizes the objective function f of x, a basic feasible solution which optimizes our objective function f of x is called an optimal solution of the problem. It is called an optimal solution of the problem. You can illustrate the things. Rewrite the following LPP in the standard form, that is maximize f of x is equal to 2x1 plus x2 plus 4x3, 2x1 plus x2 plus 4x3, and the constraints are subject to minus 2x1 plus 4x2 less than or equal to 4, then x1 plus 2x2 plus x3 greater than or equal to 5. Next 2x1 plus 3x3 less than or equal to 2, and x1, x2 greater than or equal to 0, but x3 is unrestricted. We can make how, or you can see how this problem can be write into its standard form. It is to introduce slack variables for the first and third constraints. First and third constraints are of less than or equal to type. So, to make them equality, you want to add slack variables. Let the slack variables are x4 and x6. A surplus variable is to be given for the second constraint, that is greater than or equal to 5 type, that let it be x5. Now, the constraints are changed into equations as, first one is minus 2x1 plus 4x2 plus x4 equal to 4, and the second is x1 plus 2x2 plus x3 minus x5 equal to 5, and third is 2x1 plus 3x3 plus x6 equal to 2. Here the variable x3 is unrestricted. Let us change it as the difference between two non-negative variables as x3 equal to x3 dash minus x3 double dash. Hence, the problem is to maximize f of x is equal to 2x1 plus x2 plus 4 into x3 dash minus x3 double dash subject to the equations minus 2x1 plus 4x2 plus x4 equal to 4, x1 plus 2x2 plus x3 minus x5 equal to 5, 2x1 plus 3x3 plus x6 equal to 2, and the non-negative restrictions x1, x2, here x3 dash and x3 double dash greater than or equal to 0. Since we changed this x3 as x3 dash minus x3 double dash, in the constraint also we can make that type of change. Then the second constraints will become x1 plus 2x2 plus x3 dash minus x3 double dash minus x5 equal to 5, and here 2x1 plus 3 into x3 dash minus x3 double dash plus x6 equal to 2, where the variables x1, x2, x3 dash and x3 double dash, they are the variables involved, all of them are greater than or equal to 0. Then the standard form of the problem is maximize 2x1 plus x2 plus 4x3 dash minus 4x3 double dash subject to minus 2x1 plus 4x2 plus x4 equal to 4, x1 plus 2x2 plus x3 dash minus x3 double dash minus x5 equal to 5, and third one is 2x1 plus 3x3 dash minus 3x3 double dash plus x6 equal to 2, and x1, x2, x3 dash, x3 double dash greater than or equal to 0. That is the standard form. In next case, obtain all the basic feasible solution to the set of linearly independent equations. They are x1 plus 2x2 plus 3x3 equal to 4, and 2x1 plus x2 plus 5x3 equal to 5. So, we are given two linearly independent equations. Now, to find their basic feasible solutions. Here, two linearly independent equations x1 plus 2x2 plus 3x3 equal to 4 and 2x1 plus x2 plus 5x3 equal to 5 are in three variables. They are x1, x2 and x3. Substituting one of the variable as 0, the basic solution can be obtained. For that, consider x1 equal to 0. The set of equation reduced to 2x2 plus 3x3 equal to 4, x2 plus 5x3 equal to 5. Solving these equations, you will get, by solving these two equations, you will get x2 equal to 5 by 3 and x3 equal to 2 by 3. Considering the variable x2 equal to 0, the set of equations reduced to x1 plus 3x3 equal to 4, 2x1 plus 5x3 equal to 5. Then solving these equations, we get x1 equal to 5 and x2 equal to, x3 equal to minus 1. In the same way, we can consider here x2 equal to 0. In the same way, we can consider x3 equal to 0. When we are considering x3 equal to 0, the equations becomes x1 plus 2x2 equal to 4, 2x1 plus x2 equal to 5. When solving these two equations, we will get x 1 equal to 2 and x 2 equal to 1. Hence, the basic solution of the given system of equations are: first one 0, 5 by 3, 2 by 3, 5, 0, minus 1, 2, 1, 0. These are the basic solutions. All basic solutions are non-degenerate because they contains only one 0. Now, the canonical form of equations. Let x 1, x 2, etc. x m be a set of basic variables corresponding to a system of equations a x equal to b, where a equal to a11, a12, etc., a1n, a21, a22, etc., a2n, etc., am1, am2, etc., amn. B equal to b1, b2, etc., bm transpose, and x equal to x1, x2, etc., xn transpose. Ax equal to b can be written as a11, a12, etc., a1m, a21, a22, etc., a2m, then am1, am2, etc., amm into x1, x2, etc., xm, that is equal to b1 minus a1 m plus 1 x m plus 1 minus a1 m plus 2 x m plus 2, etc., minus a1 n into xn. Next, b2 minus a2 m plus 1 x m plus 1 minus a2 m plus 2 x m plus 2, etc., minus a2 n xn. Finally, bm minus a m m plus 1 x m plus 1 minus a m m plus 2 x m plus 2, etc., minus a m n xn. The m by m matrix on left hand side is non-singular because the basic vectors, which are the columns of this matrix, are linearly independent. Pre-multiplying both sides by its inverse, we get the pre-multiplying by its inverse a here a m m, it is a square matrix, a not a m n, but a m1, a m2, etc., a m m. So, pre-multiplying by its the inverse of this matrix, we get x1, x2, etc., x m, that is equal to b1 bar minus a1 m plus 1 bar into x m plus 1 minus a1 m plus 2 bar x m plus 2, etc., minus a1 n bar x n. The next is b2 bar minus a2 m plus 1 bar x m plus 1 minus a2 m plus 2 bar x m plus 2, etc., minus a2 n bar x n, etc. The last is b m bar minus a m m plus 1 bar x m plus 1 minus a m m plus 2 bar x m plus 2, etc., minus a m n bar x n. So, we are getting a solution like this x1, x2, etc., for x1, x2, etc., xn, or x1 plus or x1 plus we can take all the negative things to this side. So, x1 plus a1 m plus 1 bar xm plus 1 plus a1 m plus 2 bar xm plus 2 etc. plus a1 n bar xn, that is equal to b1 bar, and x2 we can take all the negative things to this side, that will be equal to b2 bar. Similarly, xm plus all these negative things, that is equal to bm bar. So, that type of equation that type of equations which are equivalent to the former equation or equivalent to this equation, this called the canonical form of the equation. So, you can write that form as x1 plus a1 m plus 1 bar x m plus 1 plus a1 m plus 2 bar x m plus 2 etc. plus a1 n bar x n equal to b1 bar, and in the same way the last equation x m plus a m plus 1 bar x m plus 1 etc. plus a m n bar x m equal to b m bar. Okay. These two are equivalent equations. They are called, the second form is called the last form. This form is called the canonical form of the equations, provided all these b I bar greater than or equal to 0 for I equal to 1 2 etc. m. Corresponding to each feasible basis, we can get a canonical form and vice versa. The advantage of putting the equations in a canonical form is that the basis and the corresponding basic feasible solution can be immediately known. Since basic feasible solution should have 0 values for non-basic variables, putting x m plus 1 equal to 0, x m plus 2 equal to 0 etc. x m plus n equal to 0, in this form we get the basic feasible solution as b1 bar, b2 bar etc. bm bar, then the zeros. Next, we are considering some results on the solution of linear programming problem as some theorems. First theorem, the set SF of all feasible solutions, if it is non-empty, is a convex set. So, for an LPP, the set of all feasible solutions SF, if it is non-empty, that will be a convex set. So, we can prove it like this. Let x1 and x2 be two feasible solutions, then x1 is greater than or equal to 0 for all components and x2 greater than or equal to 0, and ax1 equal to b and ax2 equal to b. Since x1 and x2 are the solutions of the LPP with the constraint ax equal to b. Consider any convex linear combination of x1 and x2. These two are the x1 and x2 are x1 and x2 belongs to SF. We consider the convex linear combination of x1 and x2 as x equal to lambda into x1 plus 1 minus lambda into x2 for 0 less than or equal to lambda less than or equal to 1. Then ax is equal to lambda into ax1 plus 1 minus lambda into ax2. We know ax1 is equal to b and ax2 also equal to b. So, here we are getting lambda into b plus 1 minus lambda into b. This implies ax, that is equal to lambda into b and minus lambda into b getting cancelled. So, 1 into b that remains, we getting ax is equal to b. That means x is also a basic x also belongs to the set of feasible solutions SF, because ax is equal to b. If x1 x2 belongs to SF and any linear combination of x1, the convex linear combination of x1 x2 also belongs to SF, then we can conclude SF is a convex set. The next theorem. A basic feasible solution of linear programming problem is a vertex of the convex set of feasible solutions. By the previous theorem, we got the set of feasible solution SF is a convex set for a linear programming problem. Then now the theorem is a basic feasible solution of linear programming problem is a vertex of this convex set of feasible solutions. Or equivalently, if a set of vectors P1, P2 etc., Pm can be found that are linearly independent such that psi 1 P1 plus psi 2 P2 etc. plus psi m Pm equal to B, where psi j greater than or equal to 0 for j equal to 1, 2 etc. m, then xi that is equal to psi 1, psi 2 etc. psi m along with the zeros 0, which is a basic feasible solution, is an extreme point or vertex is an which is a basic feasible solution is an extreme point or vertex of the set of feasible solutions SF. You can prove it like, consider SF, that is a set of feasible solutions. Clearly xi, that is psi 1, psi 2 etc., psi m 0, 0 etc. 0 belongs to SF because psi j's are greater than or equal to 0. Suppose that it is not an extreme point, then 2 points x1 and x2 differ from xi belongs to the set of feasible solution SF such that xi equal to 1 minus lambda into x1 plus lambda into x2 or lambda into x1 plus 1 minus lambda into x2 for 0 less than lambda less than 1. That is psi j equal to lambda into x j1 plus 1 minus lambda into x j2 for j equal to 1, 2 etc. m, and 0 equal to lambda into x j m plus x j lambda equal to 0 x j1 plus 1 minus lambda into x j2 for j equal to m plus 1, m plus 2 etc. n. Since x1, x2 belongs to SF, x j1, x j2 greater than or equal to 0. Also 0 less than lambda less than 1, hence x j1 equal to x j2 equal to 0, x j1 equal to x j2 equal to 0 for j equal to m plus 1, m plus 2 etc. up to n. So, x1 that is equal to x11, x21 etc. xm1 along with the zeros 0, 0 etc. 0 the transpose, x2 equal to x12, x2 2 etc. xm2 along with the zeros the transpose. Since x1, x2 are solutions of Ax equal to b, x11 p1 plus x21 p2 etc. plus xm1 Pm equal to B. It will be number 1. And x1 to P1 plus x2 to P2 etc. plus xm to Pm also equal to B. Be number 2. Since x psi belongs to SF, we have psi 1 into P1 plus psi 2 into P2 etc. plus psi m into Pm also equal to B. Let it be equation number 3. Now, 3 minus 1 implies x11 minus I1, x11 minus I1 into P1 plus x21 minus psi 2 into P2 etc. plus xm1 minus psi m into Pm equal to 0. Let it be equation number 4. But P1, P2 etc. Pm are by hypothesis linearly independent. Therefore, equation number 4 is possible only for psi 1 minus x11 minus I1 equal to 0, x21 minus I2 equal to 0 etc. xm1 minus psi m equal to 0. This implies psi 1 equal to x11, psi 2 equal to x21 etc. psi m equal to xm1, that is x psi equal to x1. This is contradicting the assumption. Hence, x psi is an extreme point. Conversely, a vertex of SF is a basic feasible solution. Let x I that is equal to psi 1, psi 2 etc. psi n the transpose be a vertex of SF, be a vertex of SF. Then since x I belongs to SF, x psi greater than or equal to 0. Let R of the psi j's for j equal to 1, 2 etc. R of the psi j's for j equal to 1, 2 etc. n be non-zero where R less than or equal to n. Since m less than n, neither since m here m less than n, either R less than or equal to m or R greater than m. If R less than or equal to m, if R less than or equal to m, then xi is obviously a basic feasible solution, and so the theorem holds. But if R greater than m, then we may put xi as x psi equal to psi 1, psi 2 etc. psi r 0, 0 etc. 0 the transpose, where psi j greater than 0 for j equal to 1, 2 etc. r, since xi is solution of Ax is equal to b. We have, or since x here psi 1, psi 2 etc. These values are greater than 0 for j equal to 1, 2 etc. r. Then since xi not xi, but since x psi is solution of Ax equal to b, we have psi 1 into P1 plus psi 2 into P2 etc. plus psi r into PR, psi r into PR, that is equal to b. That be equation number 1. As r greater than m, the vectors P1, P2 etc. PR are not linearly independent. So, there exists alpha 1, alpha 2 etc. alpha r not all 0, such that alpha 1 P1 plus alpha 2 P2 etc. plus alpha r p r is equal to 0. Let me number 2. Multiplying equation number 2 by a constant c, we are getting c alpha 1 p 1 plus c alpha 2 p 2 etc. plus c alpha r p r equal to 0. Let it be equation number 3. Equation number 1 plus equation number 3 implies, equation number 1 plus 3 implies c into alpha 1 plus psi 1 or psi 1 plus c into alpha 1 into p 1 plus psi 2 plus c into alpha 2 into p 2 plus etc. plus psi r plus c into alpha r into p r equal to 0. Now, psi r equal to b plus 0, that is equal to b. Psi r equal to b. This is 1 plus 3. Similarly, 1 minus 3 implies psi 1 minus c alpha 1 into p 1 plus psi 2 minus c alpha 2 into p 2 plus etc. plus psi r minus c alpha r into p r equal to b minus 0, that is again equal to b. Choose c greater than 0 sufficiently small to make psi j plus or minus c into alpha j greater than 0 for j equal to 1 to etc. r. We are selecting such a c. Then we can conclude that x1, we can conclude that x1, that is equal to the column vector containing psi 1 plus c alpha 1, psi 2 plus c alpha 2 etc. psi r plus c alpha r etc. 0 etc. 0, the transpose, and x2, that is equal to psi 1 minus c alpha 1, psi 2 minus c alpha 2 etc. psi r minus c alpha r 0 etc. 0, the transpose are feasible solutions. We have now 3 feasible solutions. They are xi, now x1 and x2, which are related through, can relate them xi as 1 by 2 into x1 plus 1 by 2 into x2. That is, xi is a convex linear combination of x1 and x2. This means xi is not a vertex, which contradict our assumption. Hence, r cannot be greater than m, which means xi is a basic feasible solution. In the next theorem, we are considering the set SF. If it is non-empty, the objective function f of x has either an unbounded minimum or it is minimum at a vertex of SF. Set of feasible solution if it is non-empty. You can prove it like, there are 2 cases of SF. Number 1, SF is bounded. Number 2, SF is unbounded. We are considering only the case where SF is bounded. To prove f of x is minimum at a vertex of SF. Since SF is bounded, SF has vertices and every point of SF is a convex linear combination, or every point of SF is a convex linear combination of its vertices. Let x1, x2, etc., xp be the vertices of SF, x1, x2, etc., xp be the vertices of SF. there is a point x0 belongs to SF, x0 belongs to SF where f of x is minimum. If x0 is a vertex, then nothing to prove. Otherwise, if x0 is not a vertex, x0, if it is not a vertex, x0 can be expressed as a convex linear combination of xr for r equal to 1 to etc. p, and so x0 equal to summation r from 1 to p alpha r into pr for summation alpha r is equal to 1, where alpha r greater than 0 for r equal to 1 to etc. p. Since f of x is linear, f of x0 that is equal to f of summation alpha r x r that is equal to summation over r alpha r f of x r that is greater than or equal to summation over r alpha r f of x k, where f of x k is the that is equal to f of x k, that is equal to f of x k, where f of x k is the least of the values of f of x r for r equal to 1 to etc. p. But by hypothesis f of x 0 less than or equal to f of x k, that is f of x, this implies f of x 0 equal to f of x k, which means that f of x is minimum at x k, which is a vertex of SF. In the next theorem, if f of x is minimum at more than one of the vertices of SF, then it is minimum at all those points which are the convex linear combinations of these vertices. That can be proved as follows. Let x1, x2, etc., xk be the vertices of SF where f of x is minimum. Then f of x1 equal to f of x2, etc., equal to f of xk. Let y be any convex linear combination of these vertices, that is y equal to summation of r from 1 to k some beta r x r, where summation over r beta r is equal to 1 and beta r greater than 0, greater than or equal to 0. And since f of x is linear, f of y equal to f of summation over r from 1 to k beta r into x r, that is equal to summation of over r beta r into f of x r, that is equal to summation over r beta r into f of x1, because f of x1 equal to f of x2 etc. equal to f of xr, that is equal to f of xk, which means f of x is minimum, at y also, that is equal to, here we are getting that is equal to f of x1. This means function value at y is same to function value at x1, that means the function is minimum at the point y also. This implies the theorem that if f of x is minimum at x1, x2, etc., xk, f of x is minimum at any linear combination of these convex linear combination of these points also. Now, let us conclude this discussion here. Then we are moving to the simplest method, that is one of the method for solving the linear programming problem, that is in next session. Hope you enjoyed this session. See you next time. Until then, goodbye.